All right, so with this system in mind, let's go about considering where else we might see this in the computing world. And I would propose that we consider, as we've done in the past, that our computer is really just this grid of memory, for instance, where each of these squares represents a single byte. And I proposed a couple of times already that when we talk about a computer's memory, we can think of them as each of these squares as having an individual location. Like I spitballed back in the day that maybe this is the first byte, the second byte, the third byte, maybe this is the billionth byte. So we can number all of the bytes inside of a computer. Well, it turns out, as we'll see today in code, computers typically use numbers indeed to represent all of the bytes in their memory, and they typically use hexadecimal notation for such by convention. So what do I mean by that? Technically, if we were to start numbering these and count at 0, as most programmers would, this is byte 0, 1, 2, 3, dot, dot, dot. This is byte 15. But if I wanted to keep going, it would be then 16, 17, 18, but that's not the true in hexadecimal. So instead, in hexadecimal, once you hit the 9, you'd actually use A through F, just as I've proposed. Meanwhile, if you kept going thereafter, you would have 1, 0. But as you noted, this is not 10. This is 16 here, 17, 18, 19. And so here's where things get a little weird. I'm saying 16. I'm saying 17. And you're obviously seeing what any reasonable person would read as 10 and 11. So there's this dichotomy. And so we need some convention for making clear to the reader that, no, these are hexadecimal numbers, not decimal. Otherwise, it's completely ambiguous. And the convention there, which you might have seen in the real world, even though it's a bit weird, is just to prefix hexadecimal numbers with 0x. It's not doing anything mathematically. It's not multiplication or anything like that. Just 0x means here comes a hexadecimal number hereafter, just to distinguish it from decimal. And you can see that even though we don't have enough room for 255 bytes, you start to see patterns that we haven't even talked about yet because we're just using those two columns as the ones place, the 16s place, and so forth. Capital or uppercase is fine. All right, so with that said, let's actually do things more technically interesting, like looking back at some code that we've already seen and seeing what we can actually glean from this newfound representation of memory location. So I'm going to go over to VS Code here, where I've opened my terminal window, but no code file yet. And I'm going to go ahead and create a file called addresses.c, because I want to start playing around now with the addresses of information in my computer. And to do this, let me do something super simple first. Let me include standardio.h. Let me do an int main void, no command line arguments. And then in here, let me do exactly the line of code we just saw. Declare an int called n, set it equal to a default value of 50. And just so that the program does something noteworthy, let's have it actually print out %i\n and plug in that value of n. So this is like week 1 stuff, just creating a variable and printing out its value, just to make sure that we're on the same page. So let me do make addresses in my terminal window, enter. And when I do /addresses, no surprise, I should indeed see the number 50. But let's consider what that actually does inside of the computer now by flipping over, for instance, to this same line of code and translating it into this same grid. So here's a grid of memory, and I don't necessarily know where in the computer's memory it's going to end up, so I'm picking spots arbitrarily. But I know that an int typically is 4 bytes on most systems. And so I've used 1, 2, 3, 4 squares. And the first 4 that I assume are available are down here. And I'm calling this n, and I'm putting the value 50 in it. So literally, when you write that line of code, int n equals 50 semicolon, the computer is doing something like this underneath the hood. Might be over here, might be over there, but I've drawn it simply down there. But that means that that 50 and that variable n in particular lives somewhere in the computer's memory. And where might it live? Well, I don't really know, and frankly, I'm not going to care ultimately after today. But let me propose that if all of these bytes are numbered from 0 on down, maybe this is address 0x123 for the sake of discussion. So it's a hexadecimal number, 123. It's not 123, it's 123, but in hexadecimal, just because it's a little easy to say. But that variable n clearly must live at some address. So can we maybe see this? Well, it turns out that in C, there is a bit more syntax we can introduce today that actually gives you access to the locations of variables inside of the computer's memory. The first of these is literally an ampersand, and you might pronounce that the address of operator. Using a single ampersand, you can actually ask the computer at what address is this variable. And then the asterisk here might be known as the dereference operator, which allows you to take an address and go to it, kind of like following a map. X marks the spot. The star will take you to that location in memory so you can see what's actually there. So what do I mean by that? Well, let me go back over to VS Code here. And let me go ahead and change my program to be ever so slightly different as follows. I'm going to still declare n just as before to have the value of 50. But instead of printing out an integer per se, I'm going to print out an address. And it turns out the format code for that using printf is %p. And if I want to print out now the address of n, recall that I have these two new capabilities, the first of which is germane. The ampersand will get me the address of n. So let me go back now to VS Code, and let me make a change, whereby I'm going to change the %i to %p, which is going to show me an address as opposed to an integer per se. But I need to tell printf what address to show. So I don't want to print out n, because that's literally the number 50. I want to print out the address of n, like where is it in memory. So here I prefix it with an ampersand. And now if I go back into my terminal window, make addresses again, /addresses. I'm not going to get as lucky as seeing 0x123 probably, because I got even more memory than that in this computer. But when I hit enter, I do indeed see 0x something. And if I zoom in here, enhance, if you will, it happens to be at this moment in time on this server 0x7FFC3A7CFFBC. So it's a big address. That's a really big number if we actually did all of the math. But who really cares? It's just the fact that it exists somewhere is the only point for now. So this %p symbol that we're passing into printf as a format code is leveraging the fact that C supports what are known as pointers. So a pointer is really just an address, the address of some variable that you can even and store in another variable called itself a pointer. So what do I mean by this? Well, if a pointer is an address, we can start to tinker with the same idea as follows. Let me actually go back to VS Code once more and play around with syntax like this. So let me still declare a variable called n and set it equal to 50. But let's actually create an actual pointer, a variable whose purpose in life is not to store a boring number like 50, but the address of some value. And so the syntax for that is admittedly weird. If you want p to be a pointer, a variable that stores an address, you literally say int star, for reasons we'll sort of see. And this is different from the star I mentioned earlier, for reasons we'll also see soon. But int star p means, hey, compiler, give me a variable called p, inside of which I can store the address of an integer. What address do you want to put in there? Well, now I can borrow that same syntax from a moment ago. I can use ampersand n, which is going to say, hey, compiler, give me, or hey, computer, give me the address of n itself. Previously, I didn't bother with a variable. I just sent the address of n right into printf directly. But I can now play with it as follows. Let me go back to VS Code here. I'll clear my terminal window. And let's just play around with two variables. So int star p, so it's an asterisk, but most people would say star, equals the address of n. And now I can just tweak line 7 ever so slightly. Instead of printing out in duplicate ampersand n, I can literally just pass in p for pointer. So I've not done anything really that interesting other than add a variable, but just to show you the syntax via which you can create a variable whose purpose in life is to store one of these addresses. So let me go ahead and now and do make addresses once more, /addresses, and we should see, indeed, pretty much the same idea. The address at which n happens to be now that I've recompiled and actually run my code. But it gets a little more interesting than that. I can do one more thing when it comes to my computer's memory. In VS Code here, let me clear my terminal again. And let me see if I can perhaps kind of reverse this process. If n is 50 and p is storing the address of n, wouldn't it be interesting if I could somehow express go to the address of n and tell me what is there? So to do that, I'm just kind of undoing all of the intellectual work I'm doing here. But if I want to print out an integer at some location, I can go back to %i. Just print an integer as always. But p now is storing the address of some place. It is the treasure map, so to speak. So if I want to go where x marks the spot, the syntax for that I claimed a moment ago is star p. So star p means go to that address. Don't print the address. Go to that address and show me what's inside of the computer's memory there. So now if I go into my terminal and do make addresses and do /addresses, what should I see on the screen when I hit enter? 50. So I indeed see now 50. Now here's where it's an unfortunate choice of syntax from the authors of C decades ago. Clearly, I'm using star in two different locations. And suffice it to say, it doesn't represent multiplication in either of them. It's being used to represent addresses somehow. When on line 6, I specify a data type like int, and then I have a star, and then the name of a variable, that is the syntax for declaring a pointer, for declaring a variable that will store an address. What address? Well, ampersand n, whatever that is, ox something. When you do a star and then the name of a pointer, without specifying a type, this just means go there. So the star clearly is related to memory, is clearly related to addresses. It's unfortunate that it's the same symbol. It would have been nice if they picked maybe a different symbol for punctuation, but they mean slightly different things in that context. On line 6, we're declaring the pointer, declaring a variable called p that's going to point to an integer's location. But when I say star p, that means go to that actual location. So just try to keep that in mind, even though it's ever so slightly subtly different. So what's going on then inside of the computer's actual memory? Well, let's consider that in pictorial form again. So even though I've written the pointer in this way, int, then a space, then star p equals ampersand n semicolon. That is the conventional way. That's how you'll see it on most websites, most textbooks. Technically speaking, I will admit that it might actually be easier to understand if you actually move the asterisk a little to the left, because this makes visually, I think, it even more clear that int star is the type of the variable p, as opposed to the star being somehow attached to the variable name itself. However, you might also see it written with a space on either side, which I don't think really helps anyone. But the point is that white space does not matter in this context. And the conventional way is to do it by prefixing the variable's name with the star. And this avoids getting into trouble when you declare multiple variables at a time. But if it helps you to think about it, you can think of it as int star as being the type. It's not just an int per se. So with that said, let's consider now the canvas of computer's memory inside of which we're storing n and now p. So previously, I proposed that n is maybe it's down in the bottom right-hand corner of the screen. So n is storing the number 50 here. But technically, n lives somewhere. And for simplicity, I'm going to claim it's at 0x123 rather than the bigger actual address we just saw. But what about p? Well, p itself is another variable that I declared separately, so it's got to live somewhere in the computer's memory. And it turns out, by convention, pointers take up more space. They typically use 8 bytes nowadays rather than just 4. Why is that? Well, if you've got 8 bytes, you can count even higher. You can have even more addresses. You can have more memory in your Mac, your PC, and phone. That's a good thing. So pointers tend to be 8 bytes, which is why I've used 8 squares on the screen here. But what is actually p storing? Well, it's just storing a number. Yes, it's technically an integer, but that integer is itself should be thought of as the address of some other value. So n is down here at 0x123. P is up here at who knows what address. Doesn't matter for the sake of discussion, but its value, what it's storing with its pattern of 64 bits, is apparently 0x123. So how does this help us? Well, if you think about this a little more abstractly, who cares about what else is going on in the computer's memory? It actually tends to be helpful to think about this pictorially as being a little something like this. At the end of the day, you and I, even when we start writing code in C that uses pointers, generally you and I are never going to care about the actual addresses. Even though I showed you 0x7 something, that's not generally useful information. It suffices to know that it exists somewhere, and let the computer figure out how to get there. And so very often when talking about pointers and addresses more generally, people actually abstract them away, so to speak. So instead of literally writing on the screen or the whiteboard when discussing this, 0x123, what the actual address is, who cares what it is? It suffices that it's a value that leads me to the other value that I care about, sort of the treasure map as I described it earlier. So let's now connect this maybe a little more metaphorically. So Carter, maybe here you might have noticed that we've had for a while now these two mailboxes on the screen, on the stage. So this white one here is labeled P to represent our pointer variable. Carter's is labeled N, representing our actual integer. And what's really kind of going on here is that if I were to access the value inside of P, much like we saw it up here, that's like opening this up and figuring out what the actual value is. Now, this itself is a little arcane, 0x123. And so if we actually do this a little more metaphorically, we can maybe do this and actually point our way, if you don't mind. So here we have a big pointer. Oh, forgive me. I guess we'll use this one here. OK. So we have this big pointer that's essentially pointing at the location in memory that we care about, be it 0x123 or something else. And then if we dereference this, that is, use the star notation, star p, that's like asking Carter to go to that location, open up the mailbox, and voila, what value do you have there? Voila. Maybe a big round of applause for Carter for having practiced this beforehand with me. All right. That was mostly just an excuse to use the foam fingers today. But with that said, that's hopefully a helpful metaphor, honestly, because these pointers, these addresses, actually tend to be among the more arcane topics in C that even if things are kind of clicking right now, as soon as you start writing code involving addresses, it's easy to sort of get lost in some of the details. But metaphorically, these mailboxes are meant to represent really what's going on. Mailboxes in the physical human world have addresses. I can go to that address, open it up, and then I can go to another address by following that treasure map, if you will, or pictorially here, the arrow that's pointing from one location to another. So even though it's very weird syntax with ampersands and asterisks and the like, it's just addresses in memory, much like mailboxes in the real world. So with that said, let's maybe begin to take off certain training wheels by revisiting what what strings are as we've been using them thus far. So here's a line of code in C that we've been using since week 1, really, where I declare a string variable called s and set it equal to quote unquote hi. Now, technically, hi is 3 letters, or 2 letters and a punctuation symbol. But how many bytes is that string taking up? Is it 1, 2, 3, or was it, I'm seeing it here, it's 4. Why? Yeah, there's always a null character that even though you don't see it on the screen, that is what terminates every string we claimed a while back. So if I were to draw this, maybe hi ends up in the computer's memory down here, bottom right-hand corner. But it is indeed 4 bytes, not just 3, because secretly there's always been that null character, even though we as programmers don't often have to type it explicitly ourselves. That's what the double quotes do for us. It terminates the string with that null character. Now, recall from week 2, when we talked about arrays, we started playing around with strings as really just being arrays of characters. So we call them a string, but we could treat them as arrays of chars, so to speak. So if the string was called s bracket 0 would give us the first char, s bracket 1 the second, s bracket 2 the third. And if you're really curious, s bracket 3 would give you the last hidden null character, which we saw on the screen as just a 0 when we printed it out while tinkering with some actual code. But technically today, logically, it would seem that it's also true that hi exclamation point in the null character must clearly live at some address. They must clearly live in their own mailbox, so to speak. So maybe, for the sake of discussion, this h today is at 0x123. But recall that arrays are characterized by contiguousness from left to right. So if h is at 0x123, it must be the case that I is at 0x124, I is at 125, and the null character is at 0x126, because those are 1 byte apart. And I deliberately chose numbers here where whether it's decimal or hexadecimal, it doesn't matter. These differ by just 1 byte themselves. So that's what implies that they're indeed adjacent or contiguous in memory. But what is s then? When I declared s to be a string, what is it that's been going in s all of this time if clearly s is actually this thing here? Well, strings have kind of been a white lie for a few weeks because s itself technically is a pointer. S is the address of this string. So the string is somewhere in memory, but s itself is a separate variable that gives you a clue as to how to find all of those characters in memory. So if you had to guess, just intuitively now, if this is the string actually in memory, that is, this is the array of chars in memory, what would logically make sense to put as the value of s? A pointer, specifically a pointer to h, and how would I express that? What's the actual value? 0x123 might very well suffice as the value here of s. Now, why might that be? Well, that essentially gives you enough information to find the beginning of the string hi in this case. Now you might think, well, wait a minute, how does it know about the second character and the third character? But now if you kind of rewind in time, oh, wait a minute, maybe now the null character actually makes even more sense from week 2. Why? Because if s is technically storing the location of the beginning of the string, someone's got to keep track of where the string ends, presumably. And that's effectively the string itself, because humans decided decades ago, let's just null terminate every string with a special character. 0, all 0 bits, 80 bits specifically, but that's enough information. The sort of treasure map leads you to the beginning of the string, and then you can use a for loop, a while loop, whatever, to walk through the string, and that's what printf does, and you just stop as soon as you see that null character. So this then is what a string actually is. S is and has always been since week 1 a pointer, so to speak, that actually refers to the start of that array of characters. And frankly, again, who cares about the 0x123 specifics? We can abstract that away and actually just treat s as literally an arrow that points to the beginning of that string, because it will be rare that we actually care about where this thing physically is in the computer's memory. Now, before we see this in code, any questions on this revelation? Yeah? Yes. Have pointers gotten larger as computers' memory has increased over the decades? Short answer, yes. Like back in my day, we were limited to like 2 gigabytes of memory total. Well, why 2? Well, if you had 32-bit memory, or if you use 32 bits to represent addresses, aka 4 bytes, as was conventional, you can recall as high as 4 billion values. But generally, numbers are both negative and positive, so that halves it. So the reason decades ago computers, PCs, Macs could have no more than 2 gigabytes of memory was because literally the integers being used, the pointers being used, were only 4 bits, that is 32 bits, 4 bytes, that is 32 bits long. And so you literally you could buy more memory. You could buy a 3rd gigabyte, a 4th gigabyte, but you literally had no way mathematically to express all of those bigger locations. So it was effectively useless in that case. In more modern times, computers tend now to use 64 bits, which allows you to count crazy high, and that's more than enough to address bigger chunks of memory. Really good question. Others on memory thus far? No? All right, well, let's translate this a bit to code by going back over to VS Code here. And let me propose now that we revisit maybe a simpler string example as opposed to these integers. So let me go ahead and throw away all of this integer-related code. Let me go ahead and, for the moment, include CS50.h so that we have access to string and other things as in week 1. And let me do a string s equals quote-unquote high in all caps. And let me do a simple safety check, %s \n s, just to make sure everything works as it did in week 1. So make addresses, /addresses, and I should indeed see high on the screen. Well, let's now kind of tinker with what's going on underneath the hood. And now things can get a little more memory specific. So I'm still going to declare s as a string up here. But you know what? Instead of printing out the string itself, let me actually treat s as the pointer I claim it is. I claim a string is just an address, so I have this new syntax today, %p, to print out pointers, to print out addresses. Let's see what s actually is. Let me do make addresses again, /addresses, and there it is. It's not as simple as OX123, but it is at location OX55C6708780004. All right, who really cares specifically? But if we poke around a bit more, things might make a bit more sense. Let's do this. Let's also print out the address using %p of how about the very first character of s. So the very first character of s is known as s*0. We did that in week 2, treating a string as an array. But how do I get the address of a character? Well, I have our new symbol today, ampersand. So even though this looks like a mouthful, ampersand, s, square bracket, 0, square bracket, it's just 2 ideas combined. s*0 gives you the first character in the string s, and adding an ampersand at the beginning says, tell me what that address is. So if I recompile this code, make addresses, /addresses, even if you don't remember the value, OX whatever, what are we going to see on the screen at a higher level? Perhaps the same exact thing. Why? Well, s is just an address, but what does that mean? Well, it's just the address of its first character. And we saw that per our picture a moment ago. So can I see the contiguousness of this? Well, I'm going to resort to some copy paste just for time's sake, even though this is going to look a little silly, and I could certainly use a loop instead. But let me print out the second location, the third location, and heck, even the fourth location of, that null character. If I now do make addresses again and /addresses and zoom in, I don't really care about what these are specifically, but notice the first 2 are indeed the same because the first represents s. The first represents the first character of s, which now I reveal are exactly the same idea. And the next ones are literally just 1 byte away, ending in 5, 6, and 7, respectively. So again, the numbers in and of themselves are not useful, actionable information, but it does let us actually see what's going on underneath the hood. So just to rewind for a moment, let me actually go back to the original version where I'm printing out the string itself using %s. Let me remake addresses to make sure that, OK, it still prints out high. But what has been going on now all this time? Well, let me go back to our simple line of code that we've been using since week 1, which gave us a string called s, setting it equal to the value of high. Let me propose now that strings were indeed this white lie. And if I can unnecessarily dramatically say, here we take like the training wheels off and reveal that all this time, string is probably actually what, technically? Yeah. A char star. That was amazing. Thank you for that. So, yeah. So it's a char star, which admittedly at first glance just makes a simple idea look unnecessarily complicated. And that's why in week 1, we indeed introduced these training wheels whereby we, CS50, invented the data type called string just to kind of hide this lower level detail. If you will, string for us is an abstraction. Now that is to say, string is not a CS50 specific word. Like every programmer in the world knows what a string is. It is a sequence of characters. It is an array of characters. But in C, technically, decades ago when it was invented, they didn't decide to create an actual data type called string because, especially if they were among those more comfortable, char star is equivalent and it achieves the exact same thing, even though at a glance we didn't want to start week 1 with that lower level detail. Question here in front. Sure. Can I clarify how the star makes it a string? So we've, up until now, been just calling it a string so that S is a string, and that's a sufficient mental model. But technically, what is a string? I claimed pictorially with my grid of memory that a string is really just an address. It's really just the address of its first character. I then tried to demonstrate as much in code by using %p and showing you literally S is a value like 0x something. And literally its first character is at that same address, 0x something. So here, when I claim that string has never really existed except within the confines of CS50, technically the data type of a string is best expressed as char star. Why? Well, a string clearly can't just be a char, because a char by definition is a single character. A string, we already know, is a sequence of characters. But how can you represent a sequence of characters? You can call it a char star, which is a different data type that we're introducing today for the first time. And the star just means that S itself is not a char. The star means that S is the address of a char. And by convention, it's the address of the first char in a string. So with that said, if I go back to my actual VS Code over here, I can change literally char string to char star S. I can get rid of the CS50 library, our so-called training wheels, which has been the goal for the past few weeks, to put them on initially and then take them off quite quickly. So now this is the same program, and %s is still the same, S is still the same, everything else is still the same. All I've done is change quote-unquote string to quote-unquote char star, which obviates the need for the CS50 library. And if I now do make addresses and /addresses, hi behaves exactly as it would. So this is now raw, native C code without any training wheels, without any CS50 scaffolding that just uses these basic building blocks and primitives. Other questions on this?
Could you please clarify why we don't use the and symbol for that S as opposed to the other one?
Correct. Why don't we use the ampersand symbol for this, and though we did earlier? So in this case, there's no reason for an ampersand because the ampersand tells you what the address of a variable is. I'll concede that it probably would be a little more consistent for us to do this, which is maybe where your mind is going. Now, never mind the fact that that looks even worse, I think, syntactically. It's a reasonable instinct, but it turns out that, too, is what the double quotes are doing for you. The C compiler, called Clang, is smart enough to realize that when it sees double quotes around a sequence of characters, it wants to put the address of that first char in the variable for you. But when we had a variable like n, which we created, you have to distinguish n from its address. So that's why we prefixed n with an ampersand. But the double quotes take care of it for you. Other questions on these here addresses? No? All right. Well, beyond that, let me propose that we tinker with one other idea to see how we actually invented this thing called a string. Well, I claim that string is just char star. You've actually seen this technique before. You know, it was just a week ago that we tinkered with structures, custom data types to represent a person. And recall that we had a structure of a name and a number representing a person. But more importantly, we had this keyword typedef, which defines your own type to be whatever you want. Now, we used it a little more powerfully last time to actually represent a whole structure of a person having a name and having a number. But at the end of the day, we really just invented our own data type that we called, obviously, person. And that represented indeed this structure. But typedef was really the enabling element there. And so it turns out with typedef, you can create any number of data types of your own. For instance, if you just really can't get the hang of calling an integer an int, you can create your own data type called integer that itself is a synonym for int. Because the way typedef works, even though this one's even simpler than the struct, is you can kind of read it from right to left. This means give me a data type called integer that is actually an int. And that's the same thing that happened a moment ago. Give me a data type called person that is actually this whole structure. But an integer is even simpler. Now, most people wouldn't do this. This really doesn't create any intellectual enhancement of like the data types. But you could do it if you really wanted. More commonly, and as you'll see this in code in the future, would be not just to typedef something like an integer, but it turns out, curiously, C has no data type for a byte. Like, there's no built-in obvious way to represent of like before did this thing called a string ago that we tinkered with structures, custom data types to represent a person. And recall that we had a structure of a name and a number representing a person. But more importantly, we had this keyword typedef, which defines your own type to be whatever you want. Now, we used it a little more powerfully last time to actually represent a whole structure of a person having a name and having a number. But at the end of the day, we really just invented our own data type that we called, obviously, person. And that represented indeed this structure. But typedef was really the enabling element there. And so it turns out with typedef, you can create any number of data types of your own. For instance, if you just really can't get the hang of calling an integer, you can sure. But typedef was really the enabling element. If you call one's even simpler than the struct, is you can kind of read it from right to left. This means give me a data type called integer that is actually an int. And that's the same thing that happened a moment ago. Give me a data type called person that is actually this whole structure. But an integer is even simpler. Now, most people wouldn't do this. This really doesn't create any intellectual enhancement of like the data types. But you could do it if you really wanted. More commonly, and as you'll see this in code in the future, would be not just to typedef something like an integer, but it turns out, curiously, C has no data type for a byte. Like, there's no built-in obvious way to represent 8 bits and store whatever you want in them. However, you can use what's called a uint8_t, which is a data type that comes with C. And frankly, those more comfortable might simply use this data type once you sort of commit to memory that it exists. But honestly, for most of us, it's a lot more convenient to think of a byte as being its own data type. When you want to write code that manipulates 1 or 2 or more bytes, wouldn't it be nice to have a data type called byte? So it turns out that you can represent a byte, which is 8 bits, using an unsigned integer with 8 bits. And this is just a data type that's declared in some other C header file. But long story short, you'll see and use this before long. But it's just a synonym to make things a little more user-friendly, like person, like string, like byte. So what is in the CS50.h header file, among other things? Literally this line of code. This is the single line of code that we deploy in week 1 onward that teaches Clang to think of the word string as being synonymous with char star so that you all never have to type or know or think about char star until, wonderfully, today in week 4, a couple of weeks later instead. So that's all we've been doing. That is the technical implementation of the training wheels. It's just using a custom data type in this way. So how about one other maybe pair of examples here with our addresses such that we can tinker a little bit further. It turns out that once everything in the world is addressable using these pointers, like using numeric addresses to represent where things are in memory, you can actually do do something called pointer arithmetic. And here too, we, the programmers, generally don't care what the specific values are, but we care that they do exist. And if they do exist, we can maybe do some arithmetic on them and like add 1 to go to the next byte, add 2 to go to the next byte, add 3 to go to the next byte, and so forth. So pointer arithmetic literally refers to doing math on addresses. So how do we translate this into something actionable? Let me actually go back to VS Code here, and let me propose that we do something like the following. I'm going to throw away my first printf here, and I'm instead going to print out this string character by character, just like we did in week 2. Let me go ahead and call printf, pass in %c for a single char, \n, comma, and now I want to print out the first character in S. Using array notation, what do I type to print the first character in S? S, yep, over here. S bracket 0. So S bracket 0 gives me the first character in S. And let me copy paste just for demonstration's sake here inside of my same curly braces and print out the second char and the third. And I don't care about the null character. I just want to print the string itself for now. So even though this is jumping through way more hoops than just using %s and print the whole thing at once, it's again just demonstrating how we can, at a lower level, manipulate these strings. So let me do make addresses, /addresses. And yet again, we see, somewhat stupidly, 1 per line, HI exclamation point. I can, of course, fix that by getting rid of this. I can get rid of this. And I can leave the last \n. So let's just make it look a little prettier. Make addresses, /addresses, enter. And I can print it out all on one line. But now, using pointer notation, it turns out we can do one other thing, which admittedly for now is going to feel like unnecessary complexity. But it's actually a really helpful tool to add to our toolkit, so to speak, whereby I could instead do this. To print out the first character in S, yes, I can treat it as an array and get the 0th index. However, what is S? S is just the address of a string. What does that mean? S is the address of the first char in the string. So if I do *s, what's that going to print? Presumably H, right? Because if the first character in S is H, then *s will go to that address and show me what's actually there. And let me go ahead and do this again. Let me kind of copy paste twice and then tweak this a little bit. I want to go to the next byte over. Well, I could do S bracket 1, all right, but I could instead go to S plus 1. And I could instead go to S plus 2, thereby doing what we're calling pointer arithmetic, math on addresses. And now if I go ahead and rerun make addresses /addresses, voila, there is, whoops, I forgot my \n. Let's fix that just to be tidy. /addresses, voila, there is our high. Now, this is not how a normal person would print out a string, but it does go to show you that there's not really been any magic, like these characters are just where we predicted they would be. And now that you have this star notation, the dereference operator, which means go there, you have the ability to access individual values. You even have the ability to ask where those things are by using ampersands as well. But it turns out that the reason that we introduced the array syntax first is that the array syntax is what the world would call syntactic sugar for exactly this. When you say S bracket 0, the compiler is essentially doing *s and saving you the trouble. When you do S bracket 1, the compiler is essentially saving you the trouble of doing in parentheses S plus 1, and same for the third char as well. So all this time, pointers have been there underneath the hood. They are what allow us to go to very specific memory locations. They are going to be what allow us soon to start manipulating files, whether it's photographs of stress balls or CSI-style content. But for now, I think we should take our 10-minute break where Whoopi in the transit. See you in 10. All right, so we are back, and we've clearly drawn too much attention to the stress balls today, because now we're all out of these and whoopie pies, but more next week. In the meantime, though, we thought we'd now use some of these new building blocks, this idea of being able to manipulate underlying addresses, to revisit a couple of problems that we kind of swept under the rug previously by avoiding these problems altogether. So by that I mean this. Let me go over to VS Code, and let me create another example called compare.c, whose purpose in life in a moment is going to be to compare values in kind of a very weak one way too. So let me go ahead and include CS50.h. Let me go ahead and include standard.io.h. Let me do int main void, no command line arguments. And in here, let me just get two integers using getInt as follows. So getInt, and we'll ask for I. Let's go ahead and getInt and ask for j, just so that we have two things to compare. And then I'm going to do something super simple. So if I equals j, then let's print out, as we actually did in the past, same, \n. Else, if they're not the same, let's, of course, print out, for instance, different. So super simple program that we used the first time around really just to demonstrate conditionals. But now we'll use it to tease apart some subtleties. So let me go ahead and compile this with make compare. /compare, and we'll compare like 1 and 1 for I and j respectively. Those are, of course, the same. Let's compare 1 and 2. Those are, of course, different. So long story short, this program seems to work, and we won't dwell much further on it. But let's consider for a moment what's going on inside of the computer's memory when that code is executed. So here's my canvas of memory. Maybe I ends up over here. Maybe j ends up over here. Each of them I've drawn as 4 squares, because integers are typically 4 bytes or 32 bits. So I has the value 50 here. I has the value 50. So I accidentally typed 1 and 1, but assume that I had typed 50 in both cases. They both live at these 2 separate locations. All right, so that's all fine and good. And when we compare them, of course, 50 and 50, or 1 and 1, are in fact the exact same. But what if we actually compare different types of values? Let me go back into VS Code here. And instead of integers, let's still, using the CS50 library, maybe use some strings instead. So let me go ahead and change my I and j to maybe s and t respectively. So string s equals get string, and I'll ask for s, quote unquote, and then string t equals get string, and then I'll ask for t, quote unquote, and then down here, I'll compare s equals t. So here's the code, almost the same logically. I'm just getting different data types instead, still using the CS50 library. So let's do make compare again, /compare, and let's type in something like hi, exclamation point, hi, exclamation point, and that's interesting. All right, let's maybe try it again. So maybe lowercase, hi, hi. No, those are different. Let's do it one more time, like hi, bye. OK, so it half works, but it seems to be saying different no matter what. Well, why might that be? Well, let me first just peel back a layer. We already know that strings don't technically exist. They're really char star, and string here is char star. So does this reveal, perhaps implicitly, why s and t are being thought to be different, even though I literally typed hi twice? Yeah, on line 9 here, I'm really just comparing the addresses that are in s and t. And that's why I changed it to char star, just not to change anything, but to make it even clearer that s and t are, in fact, addresses. They're not strings per se. They're the address of the first character in those strings. And even though they happen to be the same words that I typed in, it would seem to imply that they're ending up in different places. So here's another canvas of memory for this program. And here, for instance, might be s with enough room for 8 bytes up here. As a pointer. Here maybe is where hi ended up for this particular story. Well, what's actually going in s? Well, if h is at 0x123, I is at 0x124, and so forth, what's going in s is 0x123. But when I use get string a second time and type in hi, exclamation point, even the exact same way, uppercase or lowercase, t is ending up presumably somewhere else in memory. So it's maybe using these 8 bytes over here. The same letters, coincidentally, by nature of how getString works, are ending up in the computer's memory, maybe down there, bottom right-hand corner. Those are presumably different addresses, 0x456, 457, 458, 459. So what's going to go in t as its value? 0x456, according to this example. And so when you literally compare s equals t, no, they're not the same. They are, in fact, different, even if what they're pointing at happens to be the same. So the computer's taking us literally. If you compare s and t, respectively, it's going to compare what their values actually are. And their values are the addresses of the first letter of this string and the first letter of this string, respectively. And if those addresses differ, which they clearly do, they're going to be deemed different. Now, you might wonder, well, this just seems stupidly inefficient. Why put the same string in two different places? Well, maybe the string needs to be changed later on, and we might want to have two different versions thereof. And frankly, the first time you call getString, it does its thing. The second time you call getString, it does its own thing. It doesn't necessarily know how many times it's been called in the past, and so maybe there's no communication between those calls. And so surely it's going to do the simple thing and just create more memory for each of those strings, duplicates though they may seem to be. So what does this imply? Well, you might recall that we avoided this problem altogether just a week ago by using what solution on line 9? I did not compare two strings using equals last time. Exactly. We used the stir compare function, which is in string.h very deliberately at the time, because I didn't want to trip over this mistake at the time until we were sort of ready and had the vocabulary to discuss it. But I did not do s equals t, even though logically that's what you're trying to do, compare for equality. But if you know now what a string is, it's an array of characters starting at some address. You really need something to do the heavy lifting of comparing every one of those chars from left to right. We did it ourselves last time by just implementing it in code, or 2 weeks ago, but stir compare does it for us. So stir compare s comma t actually weirdly returns 3 possible values. 0 if they're the same, a positive number if one comes before the other, or a negative number if the opposite is true. So stir comp, remember, can be used for alphabetizing things or ASCII-betizing things based on those ASCII values. So this version, if I open my terminal window now and do make compare, /compare, and type in hi and hi, now, in fact, they're the same because strcomp's doing the work of comparing them char by char. And if I do hi and by, those are now, in fact, different. So we avoided the problem last time for this very reason, that simply using equals would not have worked. Yes? Oh, good question. So when using stir compare, the documentation says that it will return 0 or a positive number or a negative number. It doesn't tell you a specific number, so the magnitude of the integer that comes back actually has no meaning. It might very well be 1, 0, and -1, but there's no guarantee. And so you can check for equality, equals, or you should check for greater than or less than, but not specific to a certain number. So it just gives you relative ordering. It doesn't give you any more detail than that. All right, so if we were to now take this lesson a step further, just to hammer home this point whereby these strings s and t must clearly live at different addresses, let's actually try to see this in code. So let me go back to VS Code here. Let me go ahead and just remove all of the conditional code and instead do something old school like print out %s\n and print out s. Then let's go ahead and print out %s again, but print out t, just to see the two strings as being duplicative. So here I go, make compare, /compare, hi exclamation point, and of course they're actually the same. But if I actually want to see where s and t are, I can change the %s to what? %p here, and I don't need to use an ampersand before the s or the t because they are already addresses. That was today's big reveal, and it turns out that printf is smart enough when you use %s and you give it an address of s or the address in t to just go there for you. So printf has been doing all of that for us with %s, but %p is actually going to print out those raw addresses. So let me do make compare, /compare, hi once, hi twice, and here now we should see the addresses at which hi lives, and it's not going to be as simplistic as 0x123 and 0x456, but if I go back to my terminal and hit enter, indeed, I get 2 different hexadecimal values that makes clear that if I were to naively compare them with equals, they're always going to be different, even if I typed in the same words. So there's implications now of this, especially if we want to start changing things in memory. So for instance, let me create a new program called copy.c. And in here, we'll start somewhat similarly with cs50.h. We'll start with standard io.h. And preemptively, I'm going to go ahead and include string.h as well. I'm going to declare main as not taking any command line arguments. And this time, I'm just going to get one string s with getString, and I'll prompt the user for s. And now let me go ahead and naively say this. Let me give myself a new string called t and just set it equal to s. My instinct being, this is how I've copied integers before. This is how I've copied floating point values before. This surely is how I copy strings, using the assignment operator as usual. Let me now, for the sake of discussion, propose that I want to capitalize the first letter in t, but not the first letter in s. So logically, based on week 2 syntax, I'm going to go into the t string, go to location 0, and set it equal to 2 upper of t bracket 0. So recall, we introduced 2 upper as just a handy function for capitalizing things. There's 2 lower, and there's a bunch of others as well. I didn't include the header file yet, though, so I'm going to go back and include, anyone remember where these are? Yeah, ctype.h, and it's fine to look that up in the manual if you ever need it. So here I am a little naively capitalizing the first letter in t. Technically speaking, I should check what the length of t is first, because if there's no characters there, if it has 0 chars, there's nothing to uppercase. But for now, I'm going to keep it simple and just blindly do that there. Now let me go ahead and print out with %s the value of s. Now let me go ahead and print out with %s the value of t. And I should see one lowercase s and one capitalized t. All right, here we go. Make copy /copy. And I'm going to deliberately type it in lowercase, hi, exclamation point. And we should see now, they're both capitalized, it would seem. Intuitively, why might that be? Exactly. The addresses are the same. So if I do use the assignment operator and just do s equals t equals s semicolon, it's going to take me literally and copy the address in s over to t, so that effectively they're pointing at the same thing. So if we draw another picture here, for instance, here maybe is s, and here maybe is the lowercase hi that I first type in down here in memory. Maybe that's at 0x123 again, and therefore that's what's in s. When I then create the variable t by declaring it to be a string as well, that gives me another variable here called t. But I'm just setting it equal to s. I'm not calling getString again in this version of copy. That was in compare. In copy, I'm just literally copying s into t. So that literally just changes the value to 0x123 also. And if we abstract away all of these addresses, that's essentially like s and t both pointing to the same place. So if I use s bracket 0 or t bracket 0, they are one and the same. So when I use t bracket 0 to use uppercase, it's changing that lowercase h to capital H. But again, both strings, both pointers are pointing at the same value. And again, this should be even clearer as of today if I go back into VS Code and indeed take these training wheels off and treat string as what it is, char star, which indicates that both s and t are just addresses, which makes even clearer syntactically that this is probably the picture that's going on underneath the hood. Now, just to make the code a little more robust, let me at least be a little careful here. If the string length of t is greater than 0, then and only then should I really blindly index into the string and go to location 0. That doesn't really solve the fundamental problem, but it at least avoids a situation where maybe the user just hits enter, gives me no characters, and I try to blindly uppercase something that's not there. But there's still a bug. There's still a bug. So how do I actually solve this? Well, it turns out we need 2 other functions that we haven't had occasion to use, but these are perhaps the most powerful, and they're going to allow us
reserve, reserve, reserve.
make the code a little more robust, let me at least be a little careful here. If the string length of t is greater than 0, then and only then should I really blindly index into the string and go to location 0. That doesn't really solve the fundamental problem, but it at least avoids a situation where maybe the user just hits enter, gives me no characters, and I try to blindly uppercase something that's not there. But there's still a bug. There's still a bug. So how do I actually solve this? Well, it turns out we need two other functions that we haven't had occasion to use, but these are perhaps the most powerful. And they're going to allow us to solve even grander problems next week when we discuss all the more things called data structures. But for now, let's very simply solve this idea of copying a string. Let me go back into VS Code here. And let me give myself one more header file that's called standard lib for standard library. So include standard lib.h, in which both of these functions, malloc and free, are declared for me. And now in my code, I'm going to behave a little bit differently here. Clearly, I got into trouble by just blindly copying the addresses. What I really want to do when I copy strings, presumably, and then uppercase one of them, is I want to create a duplicate string, a second array that is identical but is elsewhere in memory. So the way to do this might be as follows. Instead of just setting t equal to s, I should really call this brand new function called malloc, which stands for memory allocate, and it takes a single argument, which is just the number of bytes you would like the operating system to allocate for you. So whether you're using this on Windows, Mac OS, or Linux in our case, this is a way I can literally ask the operating system, please find for me some number of bytes in the computer's memory that I can now use for my own purposes. So malloc here, I technically need at least 3 bytes. But that's not going to be enough because I need a 4th for the null character. So I could put 4 here. But that's stupid. I shouldn't just hard code a number like this we've seen. So I could probably do strlang of s to dynamically figure out how many bytes I want for the copy. But that, too, is not enough because string length returns the human readable length. So hi exclamation point. So I think I want a +1 in there, too. So that just means get the length of whatever the human typed in, add 1 for the null character to make sure that we're not undercounting. Now, what can I then do? Unfortunately, I need to do a bit of work here. So let me actually go ahead now and do something like this. For int I equals 0. I is less than the string length of s, I ++. And then inside of this loop, I could copy into the ith location of t whatever's in the ith location of s. Now, this is a little buggy. One, this is inefficient to keep asking this question. We talked about this in the context of design. I should probably improve this by giving myself like a variable like n, set that equal to the string length, and then do I is less than n again and again, just so I'm not stupidly calling string length 4 different times or 3 different times. But this too is slightly buggy, and this one's very subtle. This does not fully copy s into t. Does anyone see the very subtle bug that I've introduced? Sorry? Yeah, I'm forgetting the \0. So even though I'm copying hi exclamation point or whatever the human typed in, I need to go one step further deliberately to make sure I also copy the \0 or at least manually put it in myself. So I could solve this by either doing this up to n through n, I is less than or equal to n, or I could +1 here, that too would be fine. Or if I really want, I could do this, like t bracket, the t bracket 3 equals quote unquote \0. But again, I shouldn't get in the habit of hard coding things. I could do string length of s, and that would give me the last location in s, which would also work. But that too is stupid. I might as well, or just unnecessarily complex. Let's just do this. Change one symbol, and boom. Now we're copying all 3 and the 4th character as well. All right, so with this said, let's go ahead now and make sure that t is indeed of length at least greater than 0. Then let's go ahead and capitalize t as before and print out the results. So let me go ahead and open my terminal window, make copy, /copy, and I'm going to deliberately type high in lowercase, and now we should see disparate s and t. S is now still lowercase, and t is now capitalized. But why is that exactly? Well, let me actually go into say, my computer's memory again and propose that if what I had before was this situation where S is pointing at this chunk of memory and T was accidentally pointing at that same chunk of memory, what we really want to do is have T point at a new chunk of memory, and malloc is what gives us this chunk of memory. And then using that for loop, can I copy the H, the I, the exclamation point, and even the \0. So now this is a little subtle, but malloc is what gives me access to this new chunk of memory. Malloc takes one argument, the number of bytes that you want it to find for you. Take a guess, what value is malloc returning? Conceptually, it's returning a chunk of memory, but that's like kind of hand wavy. What might malloc actually be returning?
Maybe the pointer to the first character?
Perfect. Malloc is returning the address of that chunk of memory. Not the last address, the first address. And here's a difference with strings. This chunk of memory is not magically terminated with null for you. Like I had to do that with my for loop. Malloc, and in turn your operating system, does keep track of how big these chunks of memory are. So even though it's only returning the address of the first byte of that memory, the operating system is going to know that it used up 4 bytes here, 4 bytes here, and it will keep track of that so that it doesn't give you an overlapping address in the future, because that would be bad. Your data would get corrupted. But you similarly have to remember or figure out how many bytes are available thereafter. It's up to you to manage it, as by putting a null character there yourself. So if I go back to my code now, let me actually harden this code just a little bit more as follows, whereby I can do this a little better. If I go back to VS Code here, it turns out if something goes wrong and I'm out of memory, maybe I've got an old computer, or maybe I'm typing something way bigger than 3 characters in, like 3 billion characters, and the computer might genuinely run out of memory, I actually should be in the habit of doing this. If T equals a special symbol called null with 2 L's, and I promised this would eventually exist, I should just return 1 now, or return 2, return -1, return any value other than 0, and just abort the program early. That means if malloc returns null, there's not enough memory available. And it turns out all this time, I'm going to do one other crazy thing, even though we've not expected you to do this thus far. Technically, when using getString, if you read the documentation, the manual, it too can return null. Because if you type in a crazy long string and the computer can't fit it in its memory, getString needs to signal that to you somehow. And the documentation actually says that if getString returns null, then you too should not trust what's in it. You should just exit the program immediately in this case. But there's one other improvement we can make here. And even though this is making the code seem way longer than it is, most of this I've just added is just error checking, just mindless error checking to make sure that I don't treat S as being valid or T as being valid when it isn't. Turns out this is stupid. I don't need to reinvent this wheel. Certainly for decades, people have been copying strings even in C. So it turns out there's another fun function called strcpy, wonderfully enough, that takes the destination as its first argument, the source as its second argument, and that will for me copy S into T respectively. So that does the equivalent of that for loop, including the \0. However, there's one other function, recall, that was on our cheat sheet a moment ago, whereby malloc is accompanied by one other function called free. So free is the opposite of malloc. When you're done with your computer's memory, you're supposed to give it back to Windows, to Mac OS, to Linux, so it can reuse it for something else. And frankly, if you've ever been using your computer for like hours on end, days on end, and maybe it's getting slower and slower, maybe it's Photoshop, maybe it's a really big document, generally really big files, consume lots and lots of memory. If the humans who wrote that software, be it Photoshop or something else, wrote buggy code and kept using malloc, asking for more and more memory, but they never call the opposite function free, your computer might actually run out of memory. And typically the symptom is that it gets so darn slow, it becomes annoying to use. And frankly, the mouse starts moving very slowly. Maybe the thing freezes altogether. The computer crashes. Bad things happen when you run out of memory. So in my case here, if I go back to VS Code, it's actually on me in this language called C to actually manage the memory myself, so that when I have called malloc, thereafter, I had better free that same memory. Now, I don't want to free it right away. I want to free it when I'm done with it. So frankly, the very last thing I'm going to do in my program here is called free on T, because T is what I malloced up here. So at the very bottom of my program, I should free t. And then just to be super nitpicky, let me return 0 just to signify success at this point. Now, there's a slight asymmetry, which is a little inconsistent here. Even though getString, I'm going to imply, is still allocating memory for me, it actually does use malloc. GetString and CS50's other functions are special. They manage memory for you. So you do not and should not free memory that getString returns to you. We handle all of that for you. But that's a training wheel that's going to be taken off as of this week anyway, so it's kind of moot. So not to worry. But I'm only freeing memory that I malloced. All right. Null then means what is null? It is just an address, and it's literally the address 0. So there's this theme. Like NUL, recall, was the terminating symbol, which just means the string ends here. NULL, which is not greatly named, but it's what humans went with years ago, just means that this is the address 0. And what your computer does is, even though I've been playfully saying that, oh, in the top left is address 0, and then 1, and then 2, and then 3, the address 0 is hands-off. Like it's kind of a wasted byte that your computer should never use, because the computer uses 0 as a special sentinel value, null, to signify error. So we're spending 1 byte out of billions nowadays just to make sure that there's a special symbol that's coming back that can indicate when something has gone wrong. All right, that was a mouthful. Any questions on this copying of strings, this mallocing, or this freeing? Oh, all right. So let me give you a tool with which to make some of this stuff easier so that when you make mistakes or have bugs, as you invariably will, you can chase them down without having to raise your hand, without having to ask the duck. You actually have more technical tools with which to diagnose the problem yourself. And there's this new tool that we'll introduce today called Valgrind. And Valgrind's purpose in life is to check your usage of memory for you. Admittedly, it's an older program. It's pretty arcane in terms of its interface, and there's just going to be a mess of output on the screen. But there's going to be certain patterns of mistakes that you'll notice, and I'll demonstrate a couple of them now so you can see where and how you might go wrong. So I'm going to go over to VS Code here. I'm going to create a program called Memory.c that is deliberately buggy, but it's not going to be obviously buggy at first. So by that, I mean this. Let me do include standard.io.h. Let me also include proactively standard lib.h so I can use malloc. Let me declare main with no command line arguments. And let me do something very simple. Instead of just declaring an int called x, let me be a little crazy and manually allocate this memory myself. So int x just gives me an integer, and it has since week 1. But now that I have malloc, I can kind of take control over this process. So let me declare not an int, but an int star called x. So give me the address of an integer, and let me store there the return value of malloc by asking malloc for, let's say, 4 bytes. So I know that ints are 4 bytes. If I want 4 bytes, I just tell malloc, give me 4 bytes. Now, frankly, this is a little stupid. I shouldn't just assume that the int is always going to be 4 bytes on everyone's computer. So there's this function you can start using called size of, or this operator technically, where you can say size of int. And even if you're on an older computer, for instance, really old at this point, size of int will return the correct value no matter what. You don't have to assume that it's in fact 4. But you know what? I'd actually like more than this number of ints. Let me actually treat x as an array of integers. So I could, actually, if I wanted an array of integers, I could do this. Give me 3 integers. But no, let me not do week 2 syntax. Let me do this myself as follows. Let me treat this as 3 times the size of an int. So that's technically going to give me 12 bytes. But this makes x effectively an array. And this is kind of deliberate now, because if an array is just contiguous memory and malloc returns to you a chunk of contiguous memory, you can treat what comes back from malloc as an array. And indeed, that's what we're doing as strings. We're treating chunks of memory as arrays of chars. So let me do something arbitrary here. Let me go to x bracket 1 and set it equal to 72. X bracket 2, set it equal to 73. X bracket 3, set it equal to 33. And we did this a couple of weeks ago. That's high, but in ASCII code. Let me go ahead and make memory. And it seems to work fine. Let me do /memory, and no problem. Like, there's no error messages from the compiler. There's no runtime errors when I actually run the code. But does anyone see any of the bugs thus far? What did I do wrong? Let me look a little bit back. Yeah?
Does it not know when the array ends?
It doesn't seem to know when the array ends, or more specifically, I'm not respecting when the array ends because I'm sort of stupidly starting at 1, then 2, then 3. But technically, if I asked for 3 of these things, I should have done bracket 0, bracket 1, bracket 2. And there's a second, more subtle bug that you would only know from today. Yeah? OK, I don't necessarily know when one integer ends and the next one begins. That's actually not a problem because on a given system, integers are always the same size. So the computer can be smart enough to go from here, 4 bytes this way, 4 bytes this way, 4 bytes this way. That's OK. Strings are problematic because who knows how big the sentence was that the human typed in. But there's a more subtle bug. What have I not done? I didn't call free. So I didn't practice what I just preached. Anytime I malloc, I call free. But again, per my terminal window, neither of these bugs seem obvious. You might submit this code or deploy it to your software and be none the wiser. But a tool like Valgrind can actually help you find these things. So let me increase the size of my terminal window. Let me run this command Valgrind on my program. So /memory is how I ran it a moment ago. Just like debug 50, you type before the name of your program. Valgrind, you type before the name of your program. And the output's going to look crazy, but this is useful. Why? So output's going to look crazy. You type before the name of your program. Valgrind, you type before the name of your program. And the output's going to look crazy, but this is useful. Why? So notice at the very top of this, we're just seeing what version of Valgrind we're using and what command we ran. But this starts to get juicy, and I'll highlight this here. Invalid write of size 4. Invalid write. So writing means changing information, like setting a value or assigning it a value. And this is useful here. The problem is in memory.c at line 9. So :9 means line 9. All right, so let me go back to my code, look at line 9, and oh, interesting. So invalid write of size 4. So it's cryptic, but size 4 I know is the size of an integer. So I'm probably doing something stupid on line 9 involving changing an integer. And sure enough, even though it's not super obvious, x bracket 3, oh, obviously, this doesn't exist. So I have to change the problem. 1 and 2 were OK, even though it's logically the wrong thing. Now I think this will get rid of this error. So let me actually clear my terminal. .c. So let me go back to my code, look at line 9. All right, so let me go back to right. So I'll change this of /memory, and now that error went away. There's a mess of output here, but that error went away. But this is interesting here now. 12 bytes in one blocks are definitely lost in loss record 1 of 1. So unnecessarily verbose. But the hint here is that I somehow lost some bytes, otherwise known as a memory leak. So earlier, when I described an imaginary bad programmer who kept calling malloc, 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 and never freeing, that's what's called a memory leak, where you're sort of losing track of your memory and never freeing it again. So I've definitely lost 12 bytes in one block, whatever a block is in this case. This is a little less obvious. It's up to us to notice that, oh, OK, wait a minute. Memory.c line 6 is somehow germane. Let me go back to, oh, this is where I called malloc. And Valgrind doesn't necessarily know when I should free the memory. That's up to me. But I should probably free it at the end of my function when I'm definitely done with it. Because once you free your memory, you should not touch that variable again, unless you actually change what its value is. So now, as I've done this, and this program, to be clear, does nothing useful. Like, this is just an intellectual exercise, not anything productive. Let me do make memory one last time, let's do Valgrind, /memory, and let me grow my terminal window again and hit enter. And even though it's still kind of output, it's still kind of cryptic, at least it says no leaks are possible. So now this is my own sort of teaching assistant telling me before I submit the code or before I deploy it to production in real software that at least there seem to be no memory-related errors. So Valgrind is not for logical bugs. It's not for syntax errors. It's for memory-related bugs as of today. Questions on any of that? No? OK, so what else can go wrong? We mentioned these in the past. It turns out that garbage values are a thing. And recall that if you declare a variable